All right. So tonight we're going to hear about the next rover to Mars, the Perseverance rover, which launches next month. Our speaker tonight is Dr. Roger Wiens with the Los Alamos National Lab in New Mexico. So while I'm sitting here in Houston, he's talking to us from Los Alamos in New Mexico. We're very happy to have him tonight. Roger has done Mars, obviously. He's what we call a principal investigator for what's called the SuperCam instrument on the Perseverance rover. And he was a principal investigator for a similar instrument on the Curiosity rover called ChemCam, which you may have heard of, as it uses the laser to come up with a composition of rocks and soils near the rover up to about 20 feet away, 21, 22 feet away. It can determine their compositions, which is really neat because it doesn't actually have to touch the samples. So that was quite revolutionary. That's something we're able to do. And Roger had a big, huge part of that. Also, ChemCam takes some pretty cool close-up pictures too. Very, very, very small scale images if you get a chance to see those. He was also responsible for 3 instruments on the Genesis mission. You may recall that picked up some solar wind samples and brought that back to Earth about 15, 16 years ago now. I believe it's been quite a while. And it's really showed us a lot about the composition of the sun. So Roger studies the sun, more or less. He studies Mars. He's kind of all over the solar system, I think. And one of the great things about Roger is the ChemCam instrument was a U.S. and a French space agency combined effort, and he led all of that. And it's really fun to get him watch him chat with the French scientists. It's just something you got to see. It's really great, and they work really well together, and it's nice to see. And if none of this stuff was enough to impress you, he's written a book called Red Rover. Talks about his experience as a kid and becoming fascinated with astronomy and Mars and his work on the Curiosity rover and other missions he's been involved in. And he also has an asteroid named after him, asteroid 41795 Wiens. So look that up. Maybe we have at least a shape model. I don't know how big it is. Maybe Roger can tell you. So with that, I'm going to turn it over to Roger, and we're going to hear about the Perseverance rover.
Well, thanks so much, Andy. Let me know for sure that you can hear me first. Can you hear me okay?
Yes, I can, and I forgot, I want to mention one thing to everybody. So we will have a Q&A session when Roger is finished. And to do that, just send your questions into the chat box, and I will pass those on to Roger. But we will not be taking questions till the end. So please hold your questions until the end, because I don't want to get them lost in all the other chatting that may be going on. So yes, and Roger, we can hear you.
Very good. Thanks, Andy. Andy was our outreach lead for the ChemCam instrument, and so I've gotten to know him for the last decade and greatly appreciated him. He's such a wonderful part of our team. So as you can see from this title slide, we have had the privilege of having a long series of missions to Mars, most of them rovers, and so it's not often that we get such a coordinated series of missions. And because of that, we've been able to focus from one simple thing on the first ones to more complex things, and now really focusing in on, was there life on Mars, and what kind of organics can we find on Mars, organic materials. So I'm going to walk you through these rovers first of all. So way back in 1997, Sojourner landed. It was at the beginning of the internet age, and in fact, it was an internet sensation for the few people that actually had internet back then. It was only 11 kilograms and just a little tech demo to show that we could actually do this on Mars. And it was followed up 7 years later by Spirit and Opportunity. They were twin rovers, solar powered, and one of them lasted 5 years. Spirit and Opportunity lasted almost 15 years. When they were only supposed to last about 3 months. Solar powered, just amazing rovers. They told us a lot about Mars, but there were many things that we could not understand because of the small size of the payload of that rover. And so the science community longed for having actually a large scientific set of instruments on Mars. And we got our wish in 2012 with Curiosity. And so Curiosity had over 150 pounds of payload. The arm of Curiosity weighed as much as Spirit or Opportunity itself. So this is a nuclear-powered rover that really had a lot of capability. And so this was the precursor now to the Perseverance rover. So this is our history up till now. If we look at a comparison between Curiosity on the left and Perseverance on the right, they look a lot similar. They are, in fact, somewhat twins, just born about 9 years apart. So Curiosity on the left had 10 instruments and a drill. It weighed in at 890 kilograms, so about 1 English ton. And then Perseverance was built on the same chassis, and it weighs a little bit more. It has 7 instruments and a sample cache and the helicopter. So I'm going to unpack all of that for you today. It was built on the same chassis to save some money, which it did, but it has a very different purpose for this new mission. Curiosity's mission was to assess Mars' biological potential. This was the first time that we actually had a mission to Mars that actually was looking for organic or potentially biological materials since the days of the Viking spacecraft, the very first landers on Mars back in the 1970s. So it was high time that we actually get something that could look for these biological materials on Mars. It was also had the purpose of characterizing the geology of a new landing region, and especially a very interesting one, to study Mars' past habitability in terms of the role of water. And the place that Curiosity went, which I think many of you are actually familiar with, Gale Crater near the equator of Mars, a 90-mile diameter crater, it was in fact once a large lake. And we proved that by looking at the rock record. Not only was it a large lake, but it lasted at least over about 1 million years or longer over the time that it had water. It may have come and gone somewhat, but looking at the number of layers, millimeter-sized lake bed layers going up over 1,000 feet in those layers, just showed us that this was a real long-lived lake, no question about it. And so that laid to rest some of these skeptical questions about did Mars ever really have water over a long period of time. And then it was to characterize human hazards on Mars, especially things like radiation and dust. And so Curiosity has been an amazing success. It's lasted 8 years. It is still going strong. It's going over some very interesting terrain, even as we speak. And so stay tuned to that mission. But today's discussion is going to be about Perseverance. And Percy, as I like to call him, is set to do some of the same goals, but some very different ones. And so Percy is set to explore geology of a diverse landing site. We'll show that to you. Assess ancient habitability, again, looking at things like the role of water, and then seek signs of ancient life. And that's important. It's very important in this sense that Percy has different instruments. These different instruments are always going to tell us some new details about organic materials and other things. So the instrument set is really important on Percy. It's advanced compared with Curiosity in many ways. And then it is to gather samples that could be returned to Earth by a future mission. And this is a real important purpose for Percy, and also to demonstrate technology for future robotic and human exploration. So we're going to talk about all these things in this talk today. First of all, although it's important to select instruments that are doing different things like mineralogy, chemistry, rock physical properties, the hardness of rocks, and in visual sense for what is happening, the rock layers and so on, it's also a grand optimization problem. So we really have to optimize instruments on board a rover because there's not that much power, there's not that much data volume, and there's not that much time to do all of these analyses. And so I look at this as a funnel concept. You have some instruments which by their nature can do rapid analyses. And then there's some instruments that by their nature take a long time to make an analysis. That is especially true for drill sample analyses. Just to get one drill sample on Mars takes at least a week. And that is because when looking, first of all, to Curiosity, which has been doing that, when we drive up to a place where we want to make a drill sample, first of all, we want to analyze it with the contact instruments and ChemCam and MassCam, and that takes a little while. And then sometimes there's a test hole that's drilled to see if the rock is too hard or not. Sometimes it is too hard, and we've wasted our effort up to that time. And then supposing that the drill is successful, then we go on with the drill. I'm seeing something happen here on my screen, so let me see if I can get my PowerPoint back. And so you can see that on Curiosity, we have several instruments showing these different types of measurements. So remote sensing, we've had 800,000 ChemCam spectra in 8 years with Curiosity. And so that makes measurements very rapidly. In that same time, we've had, with an instrument that's on the arm of the rover, we've had 700 APXS measurements approximately, because that arm is about 450 pounds, so it takes a little while to get that out. And so that's done more like once a week than every day. And then as we get down to the drill hole or drill sample analyses, the SAM and ChemIn instruments take about 30 measurements over the course of the mission so far. And so we've supported those fewer measurements by making sure that those measurements are made in the best places. Now, if we go to the next slide, and you'll see on the right, Perseverance has corresponding instruments. So the remote sensing has MassCam Z, it has SuperCam. In the proximity measurement category, there's Sherlock, Watson, and Pixel. And on the sample cache, or sorry, the drill sample analyses, that's really just the sample cache. And so we're not even analyzing them on Mars. We're picking them up and planning to analyze them back on the Earth. Now, on the next slide step, you'll see that Perseverance has some other instruments. It has these Mars environment instruments called META and RIMFAX. And then there's a tech demo, and those are the helicopter and MOXIE. And so I'm going to tell you about all of these instruments next. But first of all, just to point out that there is an evolution to finer scale, that we're improving the rover systematics as well as the instrumentation so that these instruments can actually analyze finer scale. For that, it's important that the arm itself be very stable. And we found out with Curiosity that it can be stable. The same thing with the mast. The mast is very stable. And so we're able to make these fine scale measurements. And so that is where we're going with these instruments on Perseverance. And you'll see that. So looking at the next slide, which shows Perseverance with all of the instruments labeled. If we go through the next several slides, it has circles showing, first of all, the yellow circle showing remote sensing, and that is SuperCam and MassCam, and they're on the mast of the rover where they get the best view from up there. Then we have the proximity instruments on the arm shown with the red circle, the next slide. And so those are Sherlock and Pixel. And Sherlock has a companion instrument, which is a camera for looking at the rocks with a very fine scale, close up. And that's called Watson. And then in the next circles, the green circles, we have META, which is the weather station that is located on the halfway up the mast of the rover, and then also on some sensors on the deck of the rover. And RIMFAX, which is located at the back end of the rover with an antenna that helps it to do this ground penetrating radar. And then finally, with the sort of purplish circles, we have the tech demo. So the helicopter up at the top, and then MOXIE down at the bottom. MOXIE is inside the body of the rover. And so going on to these instruments, the next slide shows Ingenuity. This is going to be really cool. I have to tell you the backstory on this. So this Mars helicopter, which is an idea, sort of a harebrained idea hatched at JPL, it was proposed as one of the scientific instruments for this rover. But the rover actually had categories where they were looking for different types of instruments. And this helicopter didn't fit into any of those categories. It was roundly criticized in the proposal reviews and rejected. You might think that would be end of story, but in fact, people who were in the know, you could say, knew that this would be an amazing thing to do on Mars. And so the director of JPL asked some of the directors of NASA if JPL could do this as a tech demo, and they were given the green light. And so JPL has developed this helicopter for about $50 million. And the difficult thing about a helicopter on Mars is the thin atmosphere. Mars' atmosphere is only about 1% as thick as the Earth's atmosphere. And so this is an extremely lightweight helicopter with 1.2 meter blades, over 4-foot diameter blades, and or about 4-foot diameter blades. And those blades have to spin really fast in order to get this helicopter off the ground on Mars. And so the tips of those blades are going to spin at almost Mach 1 in order to get this thing off the ground. So it's really cool. The flight durations up to 1.5 minutes, maybe longer. And it has radio communications to Percy, back to the rover. And it has to operate completely autonomously from the time it takes off to the time it lands. It's got a tiny little camera on the bottom, do some sensing, and it has a solar panel on the top that charges it up, and it can fly once a day. So we wish this helicopter demo good luck. And especially I wish it good luck for a reason I'll show you in a couple of slides. But first I'm going to show you how it's going to Mars. So this next slide shows where Percy is mounted on the rover to get to Mars. This is actually the belly of the rover. It's upside down right here. And so Ingenuity is mounted all folded up here on the belly of the rover. And that's how it's going to get to Mars. There's a cover that goes over this. That cover is going to fall off. The rover drives off a little bit to get rid of that cover. And then this whole thing folds out, drops to the ground like a baby zebra being born, and then from there it's on its own and it has to fly. So good luck to this. But like I said, I'm really excited about this, and I'll show the reason in the next slide. I think helicopters could open up new ways to explore the red planet. So if this works, I think we have a way to get at some relatively inaccessible terrain on Mars. So in the next time step or next slide, you can see this cave on Mars. This is one of the larger openings into a cave. The caves are lava tubes, and so they can stretch for kilometers or miles, many very long caves. But their main openings are usually a hole in the top, like this. And so there is no way to drive a rover into this kind of cave, no way. And you might be able to think about winching something down, but that's also extremely difficult. So for me, going into a cave like this with a helicopter seems like the best and maybe the only way to do it. And we've been developing here at Los Alamos an instrument that it would look for organic materials in that kind of environment. So on the next time step on the right, you'll see this, actually it's a cover page for an R&D 100 contest entry showing this organic ham on a helicopter going into a Mars cave. So we're dreaming big, but you know, I think this could be really cool. And so I'm really wishing this Mars helicopter demo on Perseverance. I'm wishing Ingenuity good luck. Okay, now back to Perseverance and its instruments. So on the next slide, you'll see that Perseverance has a tech demo that is really designed for astronauts and for rockets on the surface of Mars. This tech demo breathes in Mars air, which is 96% CO2 at that very thin pressure, and it converts it to oxygen and a byproduct of carbon monoxide. And it's going to store up the oxygen and then vent it off every once in a while. But this could be used for astronauts or oxidizer for rocket engines or other engines on Mars. So it uses a catalytic conversion and it uses up to 300 watts. It makes about 10 grams of oxygen per hour, and that's only about 1/4 of the needs of one human. We use a fair amount of oxygen. So these would clearly have to be scaled up for future missions, but this is the kind of thing that we would use, and it's a demo to show that it's going to work on Mars. Next slide. So this instrument is the Mars Environmental Dynamics Analyzer. By the way, MOXIE was built by or operated by MIT. The PI is at MIT on the East Coast. META is actually provided by a Spanish organization in the Spanish government, and it's going to measure the wind speed, direction, pressure, relative humidity, ground temperatures, and air temperatures, and radiation, and especially in the ultraviolet. And so here you see some of the booms that it uses and some of the surface sensors that are used to get that kind of information. And it's a step up from previous environmental stations on previous missions. Next slide is RIMFAX. So this is a radar imager for Mars subsurface experiment. And this one is actually provided by the Norwegian Defense Research Institute. And so it is to look underground on Mars. And so as the rover drives, this RIMFAX radar antenna can be operating to understand the layers of rock that are underneath the rover, or maybe even something else, possibly ice or whatever. It can go more than 60 meters, probably 100 meters down, and it's only using 10 watts. So this is a great instrument. We're excited to use it. There have been 2 radars used on Mars from orbit. This would be the first time from the surface of Mars. So good luck to this one. Next slide shows PIXL. It's an acronym for Planetary Instrument for X-ray Lithochemistry. And PIXL is a JPL instrument. It is, like I said, on the arm of the rover, one of 2 main arm instruments. And it has a high voltage power supply that produces a small electron beam that then in turn produces X-rays. And those X-rays are focused to 120 micron beam, so a very small fraction of an inch. And that beam can be rastered over a small area of the surface of a rock, and it can produce these little images that you see in the lower right that are images of the abundance maps of different elements in this material. And this is just millimeters across, these images. And it can do that on a cleaned off surface because that arm also has a rock abrasion tool to uncover and smooth off the surface of the rock. Next is the other instrument on the arm of the rover, which is Sherlock and its companion Watson. Sherlock's got the coolest acronym. It is Scanning Habitable Environments with Raman Luminescence for Organics and Chemistry. And what it does is it looks for organic materials, both through luminescence or fluorescence and through Raman spectroscopy. And it does that with a ultraviolet laser, a small laser of less than, let's see, I think it's some microjoules, and a few microjoules, and it produces fluorescence and Raman in a range that is also in the ultraviolet. And you can see some of the details there. The instrument is actually a consortium led by JPL. It has some parts from Los Alamos, some parts from like the laser from photonics, I think it is, and various other parts. Watson is on the right, and Watson is this imager that will show in fine detail what this instrument and other instruments are actually analyzing. Next is this image of the rover that shows that Perseverance has 23 cameras. Actually, a number of them are on the descent stage, so it'll separate from the rover at landing. But the rover itself still contains 16 cameras, of which 7 of them are for science purposes. Then there's others like nav cams and has cams that are really for engineering, to try to help line up the arm of the rover, to check the terrain around the rover, etc. But I'm going to take you into, we've talked about Watson already, but I'm going to take you into some of the other instruments next. So the next slide shows Mastcam Z, and the Z stands for zoom. So Curiosity had a Mastcam, but it had fixed focus cameras, and two different, or not fixed focus, but fixed focal length cameras. But the Mastcam Z has a stereo zoom that goes from wide angle all the way to telephoto. And it has normal red, green, blue filters, just like your iPhone camera. So it gets the normal color like that. But then it also has a number of filters that can be put in place through a filter wheel. And that the wavelength position of those filters are shown on the right. And you can see it covers quite a large amount of the wavelength that our eyes can see, plus a little bit into the very near infrared. And those can be used for scientific purposes to try to help understand the rock's composition over a wide area. So the next slide then goes to SuperCam. I'm going to spend just a little bit more time on SuperCam because it's my favorite instrument. It's the one that I'm in charge of. We had, as Andy said, a similar instrument in some senses on Curiosity. SuperCam has added several different techniques so that we can cover not just chemistry like ChemCam, but also mineralogy using two techniques, Raman spectroscopy and visible and infrared spectroscopy. And then we also added a microphone, which is not even shown on this proposal cover because we added it later. So let me tell you a few of the things that SuperCam does. First, we're going to go back and I'm going to show you a little bit of a clip from ChemCam just to show you how the laser-induced breakdown spectroscopy looks. So let's see, if Andy, if you can play that video that has ChemCam written on the right-hand side, I'll just say a little bit about what it's showing. So first of all, there's this animation showing that both ChemCam and SuperCam are point, focus, and shoot kinds of instruments up on the mast of the rover. Then you see that part of each instrument has a body unit. This part sits in the body of the rover and it has 3 optical spectrometers that are fed by fibers. They get that light from the mast, and this is the part that's on the mast. You can see the laser was over on the left-hand side, and in both cases, the laser fires out through a 4.5-inch diameter telescope. These are the biggest, ChemCams is the biggest on the surface of Mars, and SuperCams is about to join it. And so we focus that telescope, give it the right commands here, and then it fires the laser. The laser beam's invisible. So what you see are these flashes of plasma on these targets, and they're visibly bright. So we can see them, and that's why we can use this instrument to over 20 feet away to tell us the chemical composition. So the telescope pulls in the light from that flash, and it has the atomic emission spectrum from all of the atoms that we just shot off of that target. And by calibrating that, we get the chemical composition of 25 feet away. So SuperCam includes that same technique. And if I show you on the next slide, the number of laser shots that ChemCam has done is quite phenomenal. And I think I showed that already on one slide, that we're almost up to 800,000 laser shots. So this has been a very steady workhorse for the Curiosity rover, and it's going to be a steady one for Perseverance as well. So on the next slide, we see the what does the atomic emission spectrum look like? And this is what we call LIBS. So this is a LIBS spectrum, and you can see we have 3 spectral ranges, 3 spectrometers. Now that same thing is the case for on both ChemCam and SuperCam, and we get a lot of these atomic emission lines, and by the wavelength where they show up, we can tell what element they represent. And this was in fact the first spectrum from ChemCam on Mars. Now we're going back to SuperCam on the next slide. And so if you can turn to the slide with SuperCam on the top, you'll see the artist's picture at the top. We have both the infrared and the green beams. So you've seen the infrared beam already. It's not really visible, but in the picture we try to show it as red in the upper left. But you saw that bright spot that we see on the lower left. Now we also have time-resolved remote green Raman spectroscopy that is supported by by the laser when it is converted into a green laser. And so if we go to the next time step, you'll see that brilliant green flash. In fact, if you go and toggle back and forth between those, you'll see what it looks like when this thing is firing effectively. And that doesn't really blast the target like the LIBS laser. like the plasma, the one that creates a plasma. Instead, this one more or less tickles the surface, tickles it hard, I'm sure, but it actually excites the molecules, doesn't break the molecular bonds, at least we try not to, but instead it makes those molecules really vibrate. And if you look on the next slide, you'll see a spectrum of the Raman of the Raman signal, or the Raman light, that we get from this from this green laser. So we block off the returning green light from the laser, and we get light at a slightly longer wavelength. We categorize it or catalog it as a Raman shift, but it's slightly longer wavelength, and there are certain bands that all of a sudden there's a lot of light there, and those the position of those bands tell us the strength of the molecular bonds. And on the right-hand side, you see these little things kind of stretching back and forth. So Raman spectroscopy is especially sensitive to the symmetric stretch, which is the top one, but infrared spectroscopy is sensitive to the other ones, the asymmetric and the bend. And so SuperCam actually has both Raman and infrared, so we can get these different kind of molecular stretches. So on the next slide, you'll see the infrared spectra that we get from some of the rocks and minerals. And some of the purple bands that you see vertically in this slide indicate different absorptions in the light, the sunlight that is reflected off the surfaces of the rocks. And this wavelength is in the infrared. It's 1.3 to 2.6 microns. We have a 1.9 micron water band right in the middle. And then way over on the right, we have carbon oxygen bands. That's where you can tell it's the carbon and oxygen molecule vibrating back and forth. And so things like limestone or carbonates would give us absorptions over there. So by doing both of these mineral techniques, we really cover the range of different minerals with SuperCam. Okay, so going on to the next slide, one of the really cool features of SuperCam is that if we just left the surface untouched with the lasers and with these techniques, we would mostly see dust and the chemical and mineral composition of the dust. But in fact, that laser that gives us the plasma, when we focus that down, it creates a shock wave. That shock wave creates the sound, and it also blows the dust around, and it blows the dust away from where we are shooting. And you can see that in the inset on the left, in the upper left. And so that region is, well, that rock is about the size of a penny. So it's not very big, but it really blows the dust away from the region large enough for us to analyze with these lasers and with the infrared. And so if you look at the next time step, you'll see that there are laser pits in that region, and we just blow that dust away. And the next time step after that shows the bottom of this slide with where different places we've targeted with ChemCam, including down the drill hole. And that's important if we want to know what the composition of the drill core is that this rover is going to be collecting. So it really shows that this instrument can analyze a lot of places, even though it's way up on the top of the rover. It's not down on the arm. And in fact, remember, we can do this out to about 25 feet away. Okay, next slide. So about a year ago, right at this time, SuperCam was being installed on the rover. So I thought I'd just show a little bit about, let's see. I'm trying to remember, Andy, if since you have slides, I may not have included these slides in your slide set. So are you seeing a slide with SuperCam on the top of the rover?
No, I just see the global map of Mars.
So let's go to that one on my slide set as well. So we're synced up now again. And so here we are with the landing site of Perseverance. I like this image because when I was a kid, I actually built a telescope in time for one of the close approaches of Mars. I was my older brother helped me a lot. I was only 10 years old. And this picture always looks upside down to me, because when you look at Mars through a telescope, as you might have an opportunity to do this fall during the close approach, the telescope usually inverts the image. So I could see all of these dark bands along this equator of Mars, and in this one that's rising up here where Perseverance is, it's called Sirius Major. And Percy is right on the edge of the Isidis Basin, which you don't really see it to the right of the landing site, and then Syrtis Major on the left, that dark spot. You can see where this is relative to the other landing sites that have been on Mars. And so it's going to be a new location. Let's go to the next slide. And this shows Jezero crater. So Curiosity landed in a crater, and it was a much larger crater than this. That was 90 miles in diameter, whereas this is much smaller than that. But we could see from orbit that this crater has inlet valleys, it has an outlet valley, and so it is was another lake over 3 billion years ago, and it has a delta in it. A deltaic region and a lake are really where we would want to look for signs of organic materials or life, if there was ever life on Mars, because these rivers will bring nutrients or sediments from a large catchment area and bring it down into a small area called the delta. And so we think this is a great place to look. We're also going to look in other places around the crater and probably up on the rim and past with this rover. So next slide shows the delta, and it shows a little bit of what we can see from space on the mineralogy of this. First of all, looking at the lower part where that black arrow is, there's some evidence that there's igneous materials there, potentially from a lava flow, we don't know. And then once you look on the delta itself, we have a lot of clay minerals, smectite, which is a clay, and that's shown in blue. And then almost like a bathtub ring around the edge of this crater, we have this yellowish material, which is magnesium carbonate. And so we want to understand how these minerals were laid down the way they were. Carbonates are of special interest to us on Earth. A lot of fossils are found in carbonate sedimentary rocks. But Mars doesn't have much carbonates, and so we're not sure why, given its carbon dioxide atmosphere. So that's one of the mysteries that we hope to answer. That's kind of a side mystery, along with the question about the delta and life and so on. So let's go to the next slide. And now we're going to start to talk about the way that Perseverance is going to work to prepare the way to bring samples back to Earth. So here you see the large drill out in front of the rover. And so this is one of the major missions of this rover. On the next slide, there is actually a movie. So Andy, if you can play that movie, I'm starting mine just now. First of all, you see the drill going into the rock, then you see the drill the drill core being brought over to the rover. So that's a hollow drill, and it has rock inside of it, and there's a tube, a metal tube that's around it. There it goes down into the belly of the rover. And Andy, I don't know if you can stop the video right here. If you can see the workings inside of that whole area, what it consists of, I'm trying to stop mine. What it consists of is more than is shown in stop action in this video, because on the right-hand side, there's a number of stations for these cores. One where there's something called a core cam, which is a camera that looks inside the core or inside the tube, see if there's actually a core there. So that's important to do before we store this thing and precious cargo back to Earth. There's also capping stations, and you can see them on the right, and that's where the drill tubes get their caps. You already see that the drill material itself, that screw type mechanism, has been stripped off of this, and that was done in the carousel up above. And then on the left, you see all of the storage spaces, these drill tubes. And those drill tubes, I think there was space for 42 of them, something like that. Okay, so go ahead and finish that video. And so you'll see that, that tube being brought right up into its storage space. Thanks. Okay, so next slide. And this, let's see, and I may have changed this as well. I'm looking at a drill core, but you may not have that on your slide.
Yeah, we do.
You do, so cool. So you can see that these rock cores are housed within this, within these tubes, and so that's what we're going to get eventually. There can be a few breaks in the core, but overall it's mostly intact. And so we're looking forward to getting that. Getting the surface material is important, as well as the material that's deep inside the rock. And so these are a great way to get samples from Mars. Next slide. And here you should be seeing, are you seeing a picture of the tubes being installed inside the rover?
Yes.
Okay, cool. And so you can see this whole set going up into that whole working area of this, and this is, I believe this picture was taken in late May, so less than a month ago, or just about a month ago. These are very sterile tubes at this point because we don't want to bring any contamination from Earth and then be fooled into thinking it might be Mars microbes or something like that. So these have gone through a very rigorous pathway of sterilization. Next slide. So now we're going to talk about how the rover is going to go about its job of collecting samples. You can imagine this rover is going to land at a landing site marked with an X. It's going to go and start drilling in 1 or 2 places. And then at some point, it's going to start dropping the tubes off on the ground. And then in the next slide, you'll see that the rover may go other places. These other places may be more risky for the rover. And then, assuming that the rover makes it there and makes it back, it's going to add some more tubes to that depot, or it may start a new cache or new depot area where it adds more of these tubes. We did it this way because there was a lot of fear about the possibility that the rover could suddenly die with the tubes inside it. If that were to happen, and we'd already designed the missions to come and get the tubes, there would be no way to get the tubes out of that rover and we'd be stuck. And so it was decided that this rover needed to drop off the tubes individually. We can drop off a few at first, so we reduce the risk that we won't drop off any tubes at all if something catastrophic were to happen. And so we built up our depot or our cache over time, bringing samples back to this place. So it's going to be very fun to be following along with this rover as it starts to drill and then brings samples back. And where all does it store these samples on the surface? Now look at the next slide and you'll see that this is an artist's rendition to indicate that the rover has left these tubes on the ground here in this depot. I don't know if they'd be left all next to each other or if they're going to be spread out just a little bit like that. The area is going to be photographed extensively so we know exactly where these tubes are, even if there's a bunch of dust that comes along. And then next slide, you'll see that this big contraption that actually has a Mars ascent vehicle and another rover is supposed to come down to the surface of Mars. So that's going to be a fairly big mission. We don't know exactly when this will be yet. And then next slide, you'll see this thing unpacking with its solar arrays on each side. And then if we go on to the next slide, you'll see that there is a fetch rover that is sent out to go and get these samples. The landing site won't be right next to these samples. It could be a mile or so away. And so there's 2 possibilities. One is that the Perseverance rover is still alive and can bring the samples over itself, but the contingency is that we have a fetch rover that'll go over and grab them. And this is a pretty simple rover, but it's designed to pick up these sample tubes and bring them back. And then the next slide is showing that this fetch rover has brought the samples back to the main landing craft and is putting them into the rocket that will launch them off the surface. And the next slide shows that Mars ascent vehicle launching into a low Mars orbit. Now remember, Mars has a lot more gravity than the moon, but it has a lot less than the Earth. So it's going to take a rocket, not a huge rocket, but not a tiny rocket either. So something that we can land on Mars, and it's going to send it up. And then if we see in the next slide, that has gone into low orbit around Mars. But it's still a lot of energy to get from low orbit in Mars back to Earth. And so the best way to do that is to rendezvous with another spacecraft, transfer the sample, which it's doing right in this picture, playing catch effectively, with another spacecraft right off the side of this picture. And then that other spacecraft will bring it back to Earth with a return capsule. And so that is the plan. Perseverance is just accomplishing the first step of this kind of 3-step mission, but it's an important step, and we're so happy to be a part of it and to see this get started to bring samples back towards Earth. Okay, so the next slide shows the Atlas V rocket launching. This was actually the Curiosity rover's launch of 2012. but it should look identical for Perseverance's launch. It is now scheduled for July 20 at Cape Canaveral in Florida. And then the landing is scheduled for February 18, 2021. Of course, we've talked about Jezero crater already. So wish us a good mission. We hope that everything goes well, as always, and that we'll get there and be able to do the sampling that we want. So on the next slide, you'll see sort of a last view of the Perseverance rover with its underside, because it's already in the capsule. The top part is already in the capsule. And there's some interesting things you can see around the side. You'll see the red of the rocket engines that will help lower it to the surface. At the bottom, you see the radar receivers that will tell it when it's getting towards the ground. Right in the center, you see that black thing. That is a cover on the helicopter. And then you see the wheels all taped up to keep them sterile for Mars. So a last view, and on the next slide, that's it. So thank you very much. Thanks, Andy, for getting us through this slide set, and I'll take any questions after this.
Great. Thank you, Roger. Thank you very much. Okay, great. So we've got a couple of questions here already. So are there plans for the evolution of rover designs to accommodate future interactions and utility with on-site humans to extend or complement Mars exploration?
Oh, that's a great question. So in other words, rovers that would work alongside of humans. I think our immediate sort of ideas and plans and designs are working towards this Mars ascent vehicle and all of that. But down the road, yes, I think it's really awesome to think about how rovers and humans can work together, both on the moon and on Mars. And and of course, the Apollo astronauts used a lunar buggy, which was a rover that they could ride on. So I think we're going to see all kinds of vehicles in the future, short-term future, hopefully working to get these samples back, and in longer-term future, really working to accommodate much more sophisticated exploration. Yes.
Another question, are there already plans for the fetch vehicle and spacecraft back to Earth? Are they already being built, and how long until we could return the samples?
Yeah, so there is a program already underway to work on the plans and the development of this. It is going on at JPL. But I would have to say at this point, I think it's notional and is really working to get underway, but it's going to take a few years. I should also mention that as with these instruments, we're looking for partnership on this. It helps to defray the cost and to increase the interest around the world. And so I know that NASA is talking with European scientists and engineers about getting involvement with the European countries on all the infrastructure that's required to get samples back.
Great. Here's a question about the caves and the helicopter. Due to the depth of the caves, how do you intend to counter the lack of light and possible interrupted communications back to the rover?
Aha. Yes, so those are really great questions. The kind of mission that I envision for a first reconnaissance into a cave would be a helicopter that would go into the cave, do the reconnaissance, and come back out and land. So it basically have a landing base right at the entrance to the cave, right at the edge of the hole, so to speak, and it'd go in, do reconnaissance, come back out, and that way it could recharge up its solar cells and it could communicate back with Earth. So that would be a first way. How future work in exploration of caves goes is a good question. We could use nuclear power like we use on this rover and other things, but it's going to take more hardware to get into more sophisticated things. Now, there was a question about how life would exist in the caves. It's a branch of science, actually, how life exists. Excuse me for a second. Grab a drink. how life exists in caves on Earth. There are different forms of life in caves on Earth. And so we can see that well, there's a number of caves in New Mexico. I've been with people who have studied that. And most of that does not use photosynthesis. Those are things like rock-eating bacteria that operate in caves. And then you have other organisms that eat that bacteria. And so there's a whole food chain that lives in caves and doesn't require light. Now, photosynthesis is fairly efficient. Sunlight is a nice, efficient source of energy. So rock-eating bacteria have a lot more work to do to make energy out of that. But it works. And it turns out that those kinds of organisms are more primitive than photosynthetic organisms. And so we think that's closer to the kind of life that was on Earth several billion years ago, and the kind of life that we might find on Mars anyway. So looking in caves, I think, is just a great place to look for microbes on Mars.
Thank you, Roger. Quick question: what's the estimated launch date for the capsule retriever rover?
Yeah, so those dates have not been set yet. If you're a Marsophile like myself, you would know that missions to Mars can only happen about every 27 months. And that's because we have to wait for the planets to line up, which they are doing this year. There will be a close approach in fall. So if you start to think ahead, okay, this is 2020, next opportunity will be 2022, 2024, and then it jumps to 2027 and 2029. So I think that the powers that be are starting to look at 2027 or 2029, those kind of timeframes, because that gives this rover plenty of time to go and do its work. And it also gives us a bit more time to develop the technology, to pull together partners, and to really work to make this a reality. So we don't know for sure, that's all notional, but those are some possibilities.
Great. Take a real quick second just to remind everybody that we've been recording this presentation as well as the Q&A part, and we will put that recording up onto the LPI YouTube channel probably sometime, hopefully within the next few weeks. Another question here: has there been any progress toward building the Mars Ascent vehicle, and how many years will it take? And then doesn't the vehicle need more propulsive capability than anything of its small size ever built?
So I know that there have been some design work done on a Mars Ascent vehicle actually for quite a number of years, because we have been thinking about and dreaming about Mars sample return for a long time. How close to reality that is yet, I'm not sure. I'm not in that area. But in terms of the amount of propellant and so on that would be needed, I'm told that a rocket would only need to be about 6 feet tall or 8 feet tall, something like that, to get into orbit from the surface of Mars with a 1 kilogram, about 2 to 2.5 pound payload. And so that seems quite feasible. But a lot of work has to get done to figure out how's the best way to get samples into it. How do you keep the propellant fresh and ready to go all the way to Mars and so on? How do you mount this rocket so that it can get hoisted up into a direction that you want to launch it off into? You know, all of those kinds of things have to get worked out. So a lot of details, but it is feasible and it doesn't take too big of a rocket.
Great. Is there a way to be involved with the rover, with the mission, as a graduate student? And if so, where? University, NASA centers? Where could a graduate student be involved?
Oh, that's a great question. Yeah, I love it when people are interested in getting involved at the graduate level. Yeah, so my suggestion would be to go online, look at the different universities and institutes that are involved in the Perseverance rover science team. And in fact, maybe even contact some of the people at universities who are involved with these instruments, and see if they are looking for graduate students. And so there are many universities around the country where these people are. and also in Canada, in Europe. And good luck. Godspeed. Hope to see you someday soon.
Will the helicopter have a slow speed video camera or a high resolution still camera?
It has a small camera on board. I believe it can take fairly rapid photos. I am not part of that team, so I'm not really up on all of its capabilities, but it's I think it's more fairly, it's really in support of the flights that this helicopter has to do. But we get the pictures for free anyway. Remember, this thing has to be extremely lightweight, so it wasn't really designed to carry a payload, but there is a camera on board. And there will be some science that's probably done from that camera as that helicopter is flying.
Okay. And why is the rover so high up off the surface?
Aha. Yeah, so I'm trying to remember the exact height, but it's almost 1 meter, 3 feet off the surface. And the reason is that we don't want this rover to get stuck. That's one reason. And this rover can go over, if it was less high off the ground, you'd have to worry a lot more about, am I going to bottom out on some rock? Because the driving that's done here is sometimes done blindly. You don't want to get hung up. The other thing is that this rover is landing on its wheels, and so we don't know what's on the ground where this rover lands. The the EDL stage, as it's called, the entry, descent, and landing stage, or sky crane, has radar. The radar is going to take this and imaging, and it's going to take this rover to a place that we think is relatively benign, but it could still have fairly large rocks there. It's not going to avoid every rock. It's just going to avoid a large cliff. And so this rover doesn't want to kind of smash itself on the first rock that it lands on. And so for both of those reasons, it needs to be fairly far off the ground with its body.
Okay. I have a question about about wheels. Are there plans to use the new nickel alloy memory wheels? It's been seen testing at NASA Glenn.
Oh, that sounds like a good question. Unfortunately, I don't know. And so the wheels that Perseverance has are modified from Curiosity. Some of you may know that Curiosity's wheels have gotten kind of banged up over the 12 miles that it's gone. And so Perseverance has wheels that are going to persevere for much longer than that. They're a better design. We know that. But they're still aluminum wheels that are quite like Curiosity's. They're just a different ridge design on the wheels. So I don't know about memory nickel alloy wheels and when they might be used. But it's a great question, and since they've been developed, they might well be used sometime soon.
Great. We got just a few minutes, so I think we have time for a couple more questions. Though I know there are many more questions, so I apologize, but we do need to wrap up here in a few minutes. So another question here. With the Ingenuity platform, how was the platform tested to accurately simulate the atmosphere of Mars?
So the Ingenuity helicopter, it's difficult to test a creature like that. So this thing is supposed to fly, and it's supposed to fly in a very thin atmosphere. But now that you think about it, you couldn't just take this thing up to 100,000 feet altitude on Earth and expect it to fly there, because Earth has much more gravity than Mars. So how do you test this thing? I believe that it was tested on a tether, so that the tether took about 2/3 of the weight of the helicopter, and the rotors were supporting the other third of that weight, so that it was really simulating the amount of weight that it would have on Mars. But I'm not on the team, so I'm not exactly sure of that, but I think I saw that in a picture or two. And that was done in a pressure chamber where they had pumped it all the way down to a Mars pressure. So yeah, it's tough to test some of these things where the conditions, like both gravity and the thickness of the air, make a difference. So yeah, we think it's going to work.
Yeah, that's a really interesting question, and I know along the exact same lines, for the Mars Phoenix mission, for the Phoenix lander, for the engineering model, they had it actually tied up to a thread hanging from the ceiling during testing and during mission phase operations. So yeah,
Uh-huh.
that seems to be a consistent fix. Okay, one more question here, and it's on SuperCam, so I think it's probably a good one to end on. Concerning SuperCam analyses, would you analyze the same materials with LIBS, Raman, and IR? If so, do you have an idea of which instrument, LIBS, Raman, or IR, would analyze materials first?
Oh yeah, okay. I'm very ready to answer that question because we've worked a lot with that on SuperCam. In fact, the science definition team that I think I mentioned mandated sort of the categories of instruments and some advice for picking instruments for this rover suggested that having multiple techniques that can analyze the same spot, same fine scale spot on a target is strongly desirable. And that's because you want to sort of use a barrage of techniques on a spot, and you're going to learn much more that way. So all of the techniques are aimed in the same place with this telescope, and so our plan would be to do the LIBS first, at least with a few laser shots, because we wanted to remove the dust first. Once that dust is off, then it doesn't matter so much what technique we use first. There has been some concern that the LIBS, which blasts the target, is going to damage the surface so that the Raman or infrared wouldn't yield good results. But it turns out that the field of view that we have with the Raman and the infrared is bigger than the small spot that gets blasted with the LIBS laser. And so that's only about 5% of the field of view of the infrared and Raman. So we can pretty much do our LIBS analysis, also blows the dust away, then do the Raman and the infrared. It probably doesn't matter what order we do those in. So the main thing is to make sure we get the dust off that surface. And by the way, we take close-up images before and after so that we can see the result as well visually. So anyway, there you have it.